Hey everyone, welcome back to Math with Vansh. I'm Vansh, and I'll be teaching you math, obviously. So in this video, we're going to be covering infinite limits and limits at infinity. So if you're ready, I am too. Let's get started. So let's get started with infinite limits first. So infinite limits are basically when x is approaching one finite value, but the limit starts to approach infinity or negative infinity. So here we have the graph of 1 over x, and here we want to find what the limit of x approaches 0 is going to be. So, of f of x, sorry. So to start off, we would, without infinite limits, we would just look at the graph and see that it's approaching infinity and negative infinity, and we would just say that it does not exist. However, in infinite limits, we have to go a little bit deeper. So first, we're going to look at it from the negative end. So x approaches 0 from the negative end. So what is that going to be? I'll write it right here. So limit as x approaches 0 from the negative end of f of x. So what is that going to be? So from the negative end means from the left. So we can see that as x approaches 0 from the left, the function seems to be approaching negative infinity. So we can say that this is going to evaluate to negative infinity. And now we're going to look at it from the right. So what is the limit as x approaches 0 from the right of f of x? Now, same thing. We can see that the graph approaches, as we approach 0 from the right, we can see that f of x is approaching positive infinity. So positive infinity for that. And if we remember the definition of a limit, we remember that a limit only exists if the limit of as x approaches that number from the right and as x approaches that number from the left are equal, then only the limit exists. If they're not equal, then the limit will not exist. So since from the left it evaluates to negative infinity and from the right it evaluates to positive infinity, they're different, so that means this will not exist. So this limit does not exist. Now let's look at another similar example. And we'll just change this to 1 over x squared. So now it's going to be the same thing, except this portion of the graph right here is going to be up here now. So it's going to look like something like that, right? So now we have the function 1 over x squared. And now we want to see what the limit as x approaches 0 of f of x will be. So now we'll do the same thing. First we'll find the limit as x approaches 0 from the negative side of f of x. And here we can see that it's approaching positive infinity as we approach 0 from the left. So this is going to evaluate to infinity. And now we'll do the same thing for as we approach 0 from the right. So the limit as x approaches 0 from the right of f of x. And same thing, this is just the same as the previous example. We can see that as we approach 0 from the right, it's approaching infinity. So this is going to equal infinity. So now, since both the limits as x approaches 0 from the left and the right both evaluate to infinity, we can say that the limit as x approaches 0 of f of x is equal to infinity. Now, without infinite limits, we would just say that this value does not exist, but now with infinite limits, we can say that it values to infinity. And if we had the function 1 over negative x squared, it would be the same thing. This graph would just be flipped, and it would look something like that. And then this would evaluate to negative infinity, and this would also evaluate to negative infinity. So the limit as x approaches 0 of f of x would be negative infinity when f of x is 1 over negative x squared. Okay, so that was infinite limits. So now let's look at limits at infinity. So limits at infinity are when you have the limit as x approaches infinity of some rational function. So rational function would be like a function f of x over another function g of x. And if we wanted to evaluate this, so then how would we do that? So for this, there's three different cases rather, that there are. So the first case is when the degree of the numerator, or the degree of f of x, is greater than the degree of the denominator, or the degree of g of x. In that case, it's pretty straightforward. In that case, this limit, okay, we'll call it L for now. So in that case, this L would just equal infinity. So that would be if the degree of f of x is greater than the degree of g of x. Number 2 is where it gets kind of complicated, so I'll cover that later. But for number 3 is also pretty straightforward. In this case, if the degree of the numerator, or the degree of f of x, is less than the degree of the denominator, or the degree of g of x, then the limit would just equal 0. Okay? So that's pretty easy so far. So let's look at some examples for cases 1 and 2. So our first example can be something like the limit as x approaches infinity of 5x cubed plus 3x squared plus 2x plus 4. And then all of that over 6x squared plus 7x plus 1. Okay, so in this case, we can see that the degree of the numerator is greater than the degree of the denominator. Okay, so because in the numerator, we're starting with x cubed, and in the denominator, we're starting with x squared. So the degree of the numerator is greater than the degree of the denominator, which means that as x approaches infinity, this function will also approach infinity. So that's for case number 1, and it's pretty straightforward. So now let's look for case number 2. So case number 3. Case number 3. Case number 3 is when the degree of the denominator is greater than the degree of the numerator. So in that case, let's just do 2x squared plus 3x plus 1 over 5x cubed plus 2x squared plus 7x plus 2. So here we can see that we're starting with x cubed in the denominator and x squared in the numerator. So that means the degree is greater than the denominator than it is in the numerator. So this is just going to evaluate to 0. And this also makes sense because we can see that the function that's in the denominator is growing faster than the function that's in the numerator. So for that reason, as x gets bigger and bigger, the denominator is getting larger than the numerator more rapidly. And for that reason, this function is approaching 0. And same thing for the last case, that it's just flipped around, right? So the numerator is getting larger than the denominator more rapidly. And for that reason, it approaches infinity in the first case. Now let's look at something a bit more complicated. And this would be the second case when the degrees are equal, right? So let's look at an example such as the limit as x approaches infinity of, let's say, 3x squared plus 4x plus 1 over 4x squared plus 5x plus 2. And we want to find out what that equals. So something that we can do as x approaches infinity, and since x is approaching such a large number or such a large value, we can only focus on these higher degree terms, so 3x squared and 4x squared. And this is because those are the two terms that are really dictating how fast the function grows. Because if we look at it, suppose even with 10, right? We can see that 10 squared is going to be growing much faster than just 10, right? And as we get bigger, like numbers like 100 or 10,000, these terms become kind of insignificant. So for this reason, we can kind of just cross these out and focus on the larger degree terms. So we can make this, or we can sort of evaluate this to the limit as x approaches infinity of 3x squared over 4x squared. So you can notice how we only kept the higher degree terms and just crossed out everything else because as x approaches infinity, these terms become insignificant. So this becomes pretty easy now because now we can just cross out this x squared and this x squared, and then we'll just be left with 3/4. So this is just going to be 3/4. So that's basically how you do limits at infinity. Let me do one more example. So now suppose we had something like let's do a square root example. So suppose we had the square root of x to the fourth plus x plus 3 all over 3x squared plus 2x plus 1. Okay, and we wanted to find out what this equals. Now same thing, now it's just inside the square root, but we can still cancel out or kind of ignore the lesser degree terms. So in this case, the lesser degree terms would be this x plus 3. So we can kind of cross that out. And in the denominator, it's pretty obvious. We're just going to cross out this 2x plus 1. So now we're going to be left with the limit as x approaches infinity of root x to the fourth over 3x squared. And root x to the fourth is just x squared, right? So we're going to do x squared over 3x squared. And then, the limit as x approaches infinity. So the limit as x approaches infinity of x squared over 3x squared. And now again, we can just cancel out this x squared and this x squared, and then we'll be left with 1 over 3, or 1/3. So that would be the answer to this limit. So the main part about this that you really have to understand is that we just want to cancel out the lesser degree terms and only focus on the terms that are of the highest degree, even if they're under a square root. And that's because as x gets larger and larger, the lesser degree terms become kind of insignificant, because the higher degree terms are the ones that are really dictating how fast the function actually grows. And for this reason, we can just cancel out the lesser degree terms and only focus on the higher degree ones. So that's going to be it for this video. We covered infinite limits and also limits at infinity. Although they sound pretty similar, they're actually really different. I hope that you found this video helpful, and if you have any feedback, please let me know in the comments so I can make better content. Otherwise, I will see you for the next video. Bye bye.